Hello, this video is for Module 1 Part 3, and it includes the staring example. Alright, let's go ahead and get started with this example. The staring example comes from Rupert Sheldrake. Rupert has studied a variety of aspects regarding consciousness in animals and in people. I think the best way to describe the staring example is just to watch this short YouTube video. If you'd rather hit pause here and just play the video yourself, you can do that. For completeness, I'm going to play the video here as well.
Fields are regions of influence. It's easier to see what fields are with magnetic fields. These balls are little magnets, and as I drop them onto the plate, the balls attract each other or repel each other. They turn around, and so they all join up in patterns. There's a self-organizing property in fields. They're inherently integrative. And what I'm suggesting is that there's another kind of field called morphic fields, which organize the bodies of animals and plants and organize the activities of brains and minds.
Rupert believes that morphic fields are what allow birds to fly in perfect formation, what guide the mass migrations of herd animals. And he also believes they are the reason we get that uncanny feeling when someone stares at us. He has even run a series of experiments to try to prove that this sense is real.
Not looking.
You either look or you don't look in a random sequence of trials at somebody else, and they have to guess in each trial if they're being stared at or not.
Not looking.
The starer should concentrate their mind on the person they're looking at. When I do it, I also think of the person's name.
Looking.
So I can concentrate all my attention on them. When I'm not looking at them, I look at the floor or I close my eyes, and I think of something completely different.
Not looking.
Brilliant. 14 right and 6 wrong. Something's going on, and although the effect's not big, it's consistent and it's repeated over large numbers of trials.
Rupert has gathered a body of evidence that shows people really do appear to know when they are being stared at. For him, it supports the idea that our bodies are surrounded by morphic fields, an invisible extension of ourselves.
What I'm suggesting is that our minds work through extended fields that stretch out far beyond our heads into the world around us, linking us to other people and to our environment.
Okay, let us consider the statement that Rupert made right around the 2-minute mark in that video. And that statement was brilliant, 14 correct, and 6 wrong. So we're going to analyze that statement from a statistical perspective. Now, he did say that there appears to be the ability over a large number of trials. And here we're just looking at this one individual woman, because these are the values or outcomes that we got from that one individual woman. But the statement that was made gives the impression that this woman certainly has the ability to identify when someone's staring at her. Now let's go ahead and evaluate that statement for this woman anyway, using a statistical model. So a simulation model is going to be used to provide insight to that statement. We need to know the number of outcomes for our simulation model. Again, there's going to be 20 outcomes that were recorded. So this woman was asked to respond either look or no look over a total of 20 trials. We also need to know the probability of success, or the likelihood or chance here of obtaining a correct response. So before we determine the likelihood of a correct response, we must decide for whom is the simulation study going to mimic. Recall in the deafness example, the simulation study mimicked the outcomes from someone who was deaf. The outcomes from the subject under investigation were then compared against the outcomes we'd expect from a deaf person. Similarly, in this example, the woman who participated in the study is going to be compared against outcomes we'd expect to see if one did not have the ability to identify when someone was staring at them. So this again is going to be a 50-50 setup because the woman has a 1 out of 2 chance of correctly identifying when she was being looked at or not. So again, the number of trials is going to be 20, and the likelihood or chance of a correct response under the situation that the woman does not have the ability is going to be 1 out of 2. To determine the expected value, all we need to do is obtain the number of trials, which was 20, and multiply the number of trials by the chance of being correct, which is a 50% chance of being correct. So the number of outcomes that should be correct for a woman that is guessing is going to be at 10. So again, we are modeling a situation of a woman guessing. Similar to the deafness example, there exists inherent variation in a process that involves guessing. It is important to measure the amount of inherent variation so that we can gain an understanding of what likely versus unlikely outcomes are. So again, our goal here is to identify likely from unlikely outcomes under a particular situation. So as we've stated up above, if the woman did not have the ability, then she's going to have to simply guess at whether or not Rupert was staring at her. There's 2 outcomes here, so there's a 50% chance of being correct. As I stated up above, 10 is the expected value, and values near 10 are going to indicate no ability. So for example, if a woman had 9 correct out of 20, that probably indicates that she did not have the ability to identify in being stared at. Likewise, a value of 11 or 12 is pretty close to the expected value of 10. But values way high on the upper end of the distribution here. So if this woman was able to correctly identify, say, 20 out of 20 times that she was being stared at, then I'd believe that she would have the ability. Now, the goal of the simulation study is to determine how much inherent variation do we have in the situation where people have to guess, or where this woman has to guess. This picture that I have in the middle of the screen here, we can see that we have a lot of inherent variability. So the no ability range again is centered at 10, but here it goes all the way down to 3 and all the way up to 17. In this picture, I have a lot of inherent variability. Or am I in a situation like I have here, where the inherent variability is very small? If the inherent variability is very small, then I don't deviate very much from the value of 10. Now, one goal of the simulation study is to determine how much inherent variation we have. So am I in this situation here? Or am I in this situation here? Or am I in this situation here? It's important to determine what situation I'm in because that determines what likely values are, represented here by the different pyramids, versus unlikely values, which are on the edges. So, let's just recap here what the question is. Does 14 out of 20 provide enough statistical evidence to suggest that a woman in the video does indeed have the ability to identify when someone is staring at her? What I'm going to do with my simulation is determine whether or not 14 is an outlier against the situation in which the woman does not have the ability. So, similar to what we did before, I'm going to try to determine whether or not 14 is an outlier. In this picture, it looks like 14 is right on the edge. In the situation where I have a lot of inherent variability, then 14 is actually going to be somewhat likely, which would indicate that this woman has no ability. On the other hand, if I don't have very much inherent variability at all, then 14 is going to be an outlier and may indicate that she does indeed have the ability. Talk a little bit about simulation technologies here. So I have created a 2 AFC simulation app. The 2 is for 2 outcomes. The AFC is for alternatives. So it's 2 alternatives and then forced choice. Now this particular woman was asked to provide a forced choice. She either had to say look or no look. There wasn't a third or fourth option that she could respond with. Now that is important because a woman that does not have the ability is going to be able to get half of these correct. So the 2 alternatives allows a woman with no ability to get 10 out of 20 correct, or at least I'd expect 10 out of 20 correct. So when I compare the 14 out of 20 correct from this woman, that's not very far away from 10. So my reference value here for the value of 14 for the study outcome is actually 10, not 0. So again, when we say 14 correct, 6 wrong, that seems like she has the ability because she got many more correct. However, somebody with no ability is going to get 10 correct. So we're only 4 above somebody that has no ability. So let's talk a little bit about how to use this 2AFC simulation app here. The link for that app is provided here. I'll show you how to set that up, and then we'll talk a little bit about what the outcomes mean from that simulation. So we're going to have 2 different outcomes. Now she was going to respond with either look or no look. However, the outcome that I care about is whether or not she was correct or incorrect. So the 2 labels here are going to be correct and incorrect. This is another 50-50 example as stated. So we're going to put 50% probabilities in each of those boxes. And then the sample size, sometimes referred to as N, is just the number of trials. And then we just simply click Run Simulation. And what that's going to do is provide 20 repeated outcomes under a situation where she does not have the ability to identify when she's being stared at. So let's just recap here. There's 2 outcomes, either correct or incorrect. The probabilities are set up 50-50, and the total number of trials are 20. The tally here just indicates how many correct this individual got. So this individual right here got 11 correct and 9 incorrect. On the first trial, so right here, the woman guessed at whether or not somebody was staring at her. So again, she either said look or no look. And then Rupert had to identify whether or not that guess was correct. It looks like that guess was correct. On the second trial, again, she had to say either look or no look. She was able to get that one correct. On the third trial, she responded with either look or no look. And in this particular case, the woman got that guess incorrect. And that was repeated for a total of 20 trials here. Now this woman, the woman that we're trying to mimic with the simulation, ended up with 11 correct and 9 incorrect. We can repeat that many, many times. I showed a few outcomes here. So on the first simulation, it looks like the woman got 11 correct. On the second simulation, it looks like a woman got 9 correct, 13 correct, ... up to 10 correct. Again, all of these are being done under a situation which the woman is simply guessing. So all of these values, the 11, the 9, the 13, the 10, are outcomes that I would expect for a woman that does not have the ability, because the probabilities being specified here were 50-50. Excuse me. So we can take those values and we can just plot those out on a number line like we did before. So here you can see that I have one of the times I got a 13 correct here. Another time I got 12. Got 3 10s. Again, that's the expected. And then I also went clear down to 6 as well. Let's go ahead and hit pause here in the video, and I'll let you answer the questions that are posed there in the notes. Okay, just recapping here. How many simulated outcomes are represented in this plot? Looks like I did 10 repeated trials here. Let us consider this dot right here. So describe the process by which this value was obtained. That's question 2. That's somewhat detailed here. So this dot right here, we ended up getting 11 correct out of 20. And this was done in a situation in which a woman does not have the ability, or again was done in a 50-50 situation. So when I say describe the process, I want those 3 elements. The number correct is 11. Out of 20, there was a total of 20 trials that this woman was asked to complete. And then describe the situation in which this dot was obtained, and that was the 50-50 situation. If I was going to build a simulation in which the woman had the ability, then these dots should be shifted up much more. They should be up around 17, 18, 19, 20. Because if she has the ability, then I would expect her to get many correct. So when I ask you to describe the process, I'd need to know what situation that the dots were built under. And here, it was under a 50-50 situation. Question number 5 just asks, where is kind of your cutoff before you'd be convinced that she has the ability to identify when someone is staring at her? So these 10 dots here, again, I got these 10 dots under a situation, under a 50-50 situation. So these would be likely outcomes. Unlikely outcomes would be values up here at 15, 16, 17. In fact, out of these 10, I never saw a 14. So at least right now, a 14, a value of 14, which is what that woman in the video got, may appear to indicate that she has the ability. One thing that we're going to do is add more and more dots to this picture so that I get a better understanding of what the simulation looks like when a woman does not have the ability. And that's what we're going to do next down here. So evaluating evidence. So here I've obtained a total of 100 repeated simulations. For each simulated outcome, a total of 20 trials were conducted. These dots are centered around 10 here. So I know that this is a 50-50 setup was used for this simulation study. So let's just break that down again. The number of this is the number line for the number of correct. So there's 20 trials. We had a woman that did not have the ability attempt to identify whether or not she was being looked at. Most of the time, okay, the values are close to 10 because they're guessing. The 100 simulated outcomes means I repeated that process a total of 100 times. So again, I'll go ahead and hit pause here, and you can try to answer the following questions. Okay, just a couple of comments regarding question 8 and 9. Question 8. A statistician would have more confidence in using a graph based on 100 repeated outcomes than a graph based on 10 repeated outcomes. Why is this the case? Well, 100 repeated outcomes, again, you have a good idea of what's happening under a situation of no ability. We have a better idea of where the edges are. So it looks like it settles down around 5 on the lower end and right around 14. Okay, we did get one time, we got a value of 16, but right around 14, 15, 16, and also right around 4, 5, and 6. It looks like 7 is pretty likely to occur. The corresponding value on the upper end would be 13 from 7, and again, that one's fairly likely to occur. So where we start to see our unlikely outcomes would be out here at maybe 15 and above or 5 and below. Suppose a second statistician conducted another simulation of 100 outcomes. I would expect their cutoff to be close to mine. Why would this be the case? Again, the more dots that we have here, so it is true that we're going to have slightly different pictures. So one set of simulated outcomes might look a little different than another set of simulated outcomes. But those differences are going to become smaller and smaller if I put more and more dots on my picture. Okay, so if I were to conduct 1,000 simulated outcomes, which is fairly easy to do, okay, my picture is going to look really close to a second statistician's picture. So therefore, finding that cutoff or trying to determine whether or not 14 is an outlier, okay, is going to be, we're going to get consistent results if we base our pictures on many, many simulated outcomes. Okay. That does it for the video for Module 1, Part 3. Thank you.